So first, I really want to join everyone in thanking the organizers. It's really been an extraordinary week, and I can't imagine the effort that's gone into making this week happen. So thank you so much. It's wonderful to be here, and I'm also grateful to the open-mindedness of the organizing committee in this session on cooling beyond atoms. And so, what you'll see in the next talks is cooling of molecules, including polyatomic molecules. But here, we're actually going to talk about cooling nanoparticles in ion traps, but not ions. These are nanoparticles. And you might be thinking to yourself, I came to ICAP to hear about atomic physics. Nanoparticles don't sound to me exactly like atomic physics. So I want to tell you 3 places where you're going to find the atomic physics in this talk. And so what I want to emphasize is that the techniques we're going to use here are those originally developed for atomic physics. And what I hope that you can find interesting here is various examples throughout this talk of how the techniques that you know and love are being adapted into a different setting. And this is going to include not just the use of ion traps, like you see in this picture, but 2 different kinds of cooling methods that we've experimentally demonstrated, and a 3rd approach to cooling that's been used with trapped ion systems before, and we've proposed for nanoparticle systems. Second, there's really a commonality of goals here. So you can think of these experiments with nanoparticles as an alternate route to investigate, on one hand, fundamental quantum mechanics in ways that we're often interested in doing with atomic systems, and also to apply those quantum systems, in particular to apply superposition and entanglement, not yet, but in future experiments, to applications such as quantum sensing and transduction. And finally, as an outlook, I'd like to sketch out for you a role for future hybrid systems of atoms and nanoparticles together. So in this talk, we'll be talking about a nanoparticle in a linear Paul trap. So just to be really concrete here, we're talking about a silica particle, something like 2 times 10 to the minus 17 kilograms. You should picture it as having something between 200 and 2,000 fundamental charges, about 300 nanometers in diameter. And we're focusing here on the center of mass motion of this particle. And so this is a camera image of a particle that's oscillating back and forth along one axis. We've cooled the other axis down, and we kind of kicked it in one axis. So you can just, and yeah, we're taking a picture over a long enough time that you can see its kind of turning points here. So this is a really nice oscillator. In fact, as I'll show you in a little bit, it has a quality factor of something like 4 times 10 to the 10. And our intermediate term goal for these high Q oscillators is to prepare and control quantum states of this center of mass motion. What this talk is going to be about is about the classical steps to get us there. So with these particles, we're not yet in the quantum regime, but I want to show you how we can get there, and in particular, how we can take advantage of the techniques developed for atomic ions. So today, I'm going to first describe to you the state of the art for experiments with these kind of levitated optomechanical systems. Then I want to show you how we can load these particles into an ion trap in ultra-high vacuum. Then I want to show you how we can efficiently detect and cool the particles via a method known as self-homodyne or self-interference. In the 4th part, I want to present to you another approach to cooling using sympathetic cooling. And finally, as a brief outlook, I'll talk about how we can now bring in atomic spins in the future. So how should we think about the state of the art for these kind of nanoparticle systems? Well, in general, before we even start talking about levitation, let's just talk about optomechanics. And so optomechanical systems here, these are experiments that span a beautifully wide range of experimental platforms from the nanoscale. So this is an experiment from Oscar Painter's lab from about 10 years ago, where the motion of this kind of tiny little bar was cooled down to its motional ground state. And then here on the other hand of the spectrum, from the nanoscale to the kilometer scale, we have these LIGO mirrors, and the light in that LIGO cavity interacting with the motion of the mirrors. And so what's common to all these experiments is we're talking about interaction of light with motion, with mechanical motion, and the quantum aspect would be to look at that in the quantum regime. And for any physical system where you're talking about mechanical motion interacting with light, and you want to look at that quantum mechanically, there's going to be the challenge about coupling to the environment, because somehow you have some kind of physical coupling. For example, look at this little nanobar. It's tethered to its surroundings. The LIGO mirrors are also suspended, and that's going to provide a route for decoherence. So about 10 years ago now, back in 2011, there were actually 3 papers that came out within the span of a few months, all of them proposing that you should just, instead of trying to minimize this coupling, let's just get rid of the coupling to the environment altogether by levitating particles, whether that's optically, electrically, magnetically. So these 3 different papers from many well-known people in our field highlighted this idea of levitation, in particular decoupling from the environment, which gets us away from mechanical contact and means that these kind of quantum experiments would be possible at room temperature. It also brings us into a low damping regime where we have the possibility for these kind of ultra-high Q factors that I've already shown you. And finally, the fact of this, we can decouple from the environment offers up the prospect for long coherence times, which when we're thinking about future exotic quantum states can be really helpful. So 10 years later, this is now a science review that came out last year, sketching out the route for these levitated particles towards the quantum regime. So this is a roadmap starting with preparing particles in the ground state and describing how from the ground state it would be great to then prepare non-classical states, prepare motional entanglement of these nanoparticles, and then move on to large quantum delocalizations and even macroscopic quantum superpositions. So these are concepts that you're familiar with from the atomic world, and now this is a vision for mapping those systems to nanoparticles. Where are we now? There are now 2 experiments here that have put these particles in the bound state of their motion, and that's why this is the time to kind of look forward at the next steps. So just to show you these 2 experiments, these are 2 experiments in which particles are confined optically. The first one on the left is from Markus Aspelmeyer's group in Vienna, and on the right from Lucas Novotny's group at ETH Zurich. And so this one is about cavity cooling by coherence scattering that prepares a particle in its ground state. The second one uses feedback cooling in an optical tweezer. And so what you should know here is that both of these particles are then confined in optical traps, and these different methods are used to bring them into their motional ground state. So that sounds good. It's a starting point for doing further experiments, and these are beautiful, beautiful results, but there are drawbacks to optical cooling, in particular decoherence via direct scattering and decoherence via particle heating. So there's a really nice motivation to levitate particles not optically, but in an ion trap where we can get rid of light-induced decoherence. We have deep trapping potentials, and we have large trap volumes. We do have to face reduced optical access due to the electrodes of the trap, and the fact that we have a large trap volume means that you're not going to use a really tightly focused beam with a large NA to capture information about the particles. So we have some new challenges, but also a real motivation to use ion traps. In particular, we're going to here look at secular frequencies, secular motion at effective potentials of about with kilohertz frequencies. This means we're going to drive a trap with something like 10 kilohertz frequencies. Okay, so how do we load these particles into a Paul trap? Well, what we do is we take a metal foil, we evaporate nanoparticles onto it. So this is a picture of some nanoparticles on a Paul on this foil. Then we come in with a pulse laser from the other side. That creates an acoustic wave that throws the particle off. Luckily, also charges them in the process, so the particles are desorbed and are flying towards our ion trap. We can verify that actually, yes, the particles leave the foil, and more importantly, we can see them get trapped in our ion trap. So we turn on the ion trap only as the particles cross, so that we can capture them. And we can see that their motion gets damped. So here in a picture at kind of 10 to the minus 3 millibar, we see the damping, which is consistent with background gas cooling. We can do this then at lower pressures, and we also see that they get damped more slowly. So this is a picture where I've speeded up the damping so that we don't have to wait for half an hour to look at this picture. So this takes 30 minutes. If we're going to do this at the kind of UHV pressures we'd like, clearly that's not going to be a time we're willing to wait. So instead what we do is we use buffer gas cooling with nitrogen to, so we prepare a really clean system, but we do use nitrogen to damp down the particles. Then we pump out the nitrogen as kind of on the scale of a day. So here we have localized particles at something like 10 to the minus 11 millibar. So this is a picture of a particle. And some recent results, we've looked at then the quality factor of this oscillator. So here's a picture where I'm plotting time in seconds. So 10 to the 5 seconds is something like a week. And so this was really fun, where we you kind of kick this oscillator in one direction, you look at it oscillating, and essentially what this plot is saying, the upper line here at 7 times 10 to the minus 11 millibar, is that when you come back a week later, it's what it's still doing in the trap. It's still just kind of bouncing back and forth with roughly the same amplitude. It's gone down slightly. So this is like a line width of 35 nanohertz, and then the other curve that's plotted here was for a slightly worse pressure, 10 to the minus 9 millibar, where it kind of damps within something like a day. That's about sort of the amplitude here. The frequency is drifting around because this is a case where we're just kind of plugging in a function generator. We're not stabilizing the frequency. So that's why if you make a Allen deviation plot, you see you see a turnaround at sort of scales of kind of 100 seconds, which is about our frequency drifts. We know we could feed back to stabilize that if we want. The reason these pressures haven't been reached before with optical traps is people are using loading techniques that aren't UHV compatible. Finally, what I want to show you in this question about loading is that recently we've transferred particles between a Paul trap and an optical trap. So you do have that kind of flexibility with these different trapping mechanisms for particles. This is an experiment where we had both a linear Paul trap and a dual beam optical trap. Here you see a particle that is trapped first only by the Paul trap, which is a larger trapping volume. So somehow we're looking in this voltage. I'll tell you a little more about detection in a second. We have a signal that's telling us about the motion of the particle, and now we turn on the optical trap, transfer the particle to the optical trap. It's much tighter, so it has a much smaller motion, and so we can kind of shift the particle back and forth. We did this at relatively high pressures because in this case we only had feedback cooling along one axis, and this was work with a microparticle. But it could certainly be extended to nanoparticles and to lower pressures. Okay, so you know now how we can put these nanoparticles into a trap at ultra-high vacuum. And so let me tell you how we can efficiently detect their motion and use that detection signal to cool down the particles. The key principle about detection is that detection of these nanoparticles is based on optical interference between, on the one hand, an illuminating light field, and on the other hand, the light that's scattered by the particle. And so as the particle moves, you're going to generate an interference signal between those two fields, and if you detect that, you can collect information about the position of the particle. I'm not going to go into much more detail beyond that now. I'm happy to talk more about that later on if you want. But yeah, we can detect via interferometric methods, and we can cool effectively taking a signal from that position signal and using it to push the particle, to slow the particle back down, using what's known as cold damping. And if we want to efficiently cool, we're going to need efficient detection. So what we've previously demonstrated is these kind of standard techniques for nanoparticle detection and cooling, again with an illuminating field and the motion of the particle. But we also know that for these nanoparticles in a Paul trap, that's not going to be sufficient for us to reach the ground state, in particular because of the numerical aperture limitations of our electrodes in our Paul trap. So we went back and thought about what's been done with trapped ions, and in particular, I think this was a really nice project that came out of a discussion between one of Rainer Blatt's postdocs, Giovanni Cerchiari, and my PhD student, Lorenza Dania, who were thinking then about an experiment that was done in Rainer's group more than 15 years ago now, cooling a barium ion via self-interference. This is a picture from that 2006 paper. Let me quickly walk you through it. There's a barium ion. It's moving around in a trap. Some of the light gets, the fluorescence goes here to the right-hand side. Some of the fluorescence goes to the left-hand side. It's reflected off a mirror and then goes to the detectors after reflection. So what we see at this mirror is interference between fluorescence along these two paths, and that modulated fluorescence, modulated by the particle's motion, provides information about where the particle is. That can be used to feed back, which you see in these electronics here, to cool the ion, and which is applied via the electrodes. And in Rainer's group, that was later applied to thermometry and even to demonstrate single phonon sensitivity. But we realized, that's not just for ions. We can do that with nanoparticles. And so here's the concept. We put a mirror here next to our nanoparticle, and so down in the bottom left, what you see is that we're adjusting the mirror to make sure that the signal comes back onto the nanoparticle, and you can see that here in this video where we're just aligning the system to match the reflected signal back onto the particle. And then once we've kind of aligned this image of the particle with the particle itself, then we can scan the mirror position. And so we sit here now halfway on the slope where we get the strongest signal. And we park ourselves there to lock the cavity length, or half cavity, to lock the position of the mirror. And then that gives us a locking point, and now we can look at the signal, so we're stabilizing thermal drifts. The very fast motion you see here is micromotion of the ion trap, and the slower motion gives us position information. So we took that signal, and now what we're doing is we take the motional signal, we look at a power spectral density, and that's what's plotted here. Whoops, let me go backwards. So above, I'm just showing you this idea of this particle's image, the image of the particle from the mirror with the original particle, and both of them going to a quadrant photodiode. What you see here is a power spectral density as a function of frequency. This is kind of a standard detection method in purple, and with this homodyne method, you can see that we go down here 38 dB in terms of detection. We can see all sorts of structure that we couldn't see before. And some of these kind of key peaks are well, you see some micromotion sidebands and the drive frequencies. But the point is that we get much higher resolution and information about the particle motion. I should point out that this is, we're not comparing exactly apples to apples here because we use different frequencies for the light. So it would be about, if everything was the same, it would be about 26 dB and not 38 dB, but still a really serious improvement. Then we use this nice detection signal to implement feedback cooling. So we take the signal, we shift it by pi over 2, and we use it to damp the motion via electrodes near the trap. And so what you see here is then, again, a power spectral density, and then as the blue gets deeper and deeper, we're turning up the electronic gain on the feedback, so the peaks are getting broader and shorter, a sign of cooling. They're also shifting in frequency because we happen to be sort of rotating the axes here. And we can look at now the temperature here corresponding to this cooling. So if we use the signal that's in purple, then the temperature goes down as we turn up the gain, but then swings back up again as we have back action start to play a role. On contrast, if we're using this self-homodyne method here, this is the blue line, we just kind of keep cooling and that goes down and gets better. In this case, our final temperatures were in the kind of millikelvin regime. That was limited by the pressure in this experiment, which was kind of 10 to the minus 7 millibar. It was a setup that we'd originally built for a master's project. But we're confident that if we kind of map this setup now into our ultra-high vacuum chamber, we think that also bringing the mirror into the vacuum chamber should allow us to reach the ground state. So that was a story about a new method that we've used, or rather, quite an old method for ions that we've now brought into this nanoparticle world. And now I want to tell you about a second approach to cooling. And so you may ask yourself, well, that sounds like a good idea. This cooling you already told me about. Why do I want to hear about more cooling? And this is because if we use sympathetic cooling, it opens up possibilities to look at multiple particles in a trap and only talk to one of them. So we've already heard about sympathetic cooling this week in the context of trapped ions for metrology, also for quantum information processing. And this is the idea that the ions are coupled via Coulomb interaction, and you can, in fact, cool one of these, or one species, one kind of ion, and because of their coupling, then they will all feel this cooling force. So in particular, we could imagine having here, this is kind of a silica particle, but what if we wanted to put more exotic particles, for example, say like a nanodiamond in this trap, and you could cool only the silica particle, but also cool the nanodiamond at the same time. Why would you want to cool only the silica particle? Because when you put nanodiamonds in traps, people have seen problems like they burn up and they disappear and they graphitize. So this is not a problem we know with our rubidium atoms or calcium ions, but this is a problem for nanoparticles. Sympathetic cooling would help with that. Sympathetic cooling also provides a route to cool multiple nanoparticles in the same trap. So again, the concept is that you have a Coulomb repulsion and a shared harmonic potential, and so those two things together give you this coupling between particles or ions or anything charged in your ion trap. And what we're going to do is apply a damping force to one particle. So here's the picture. Those are the two particles. We're going to use a collective laser field to detect the motion of the particle. But we're going to apply feedback to only one particle. And I should be clear that we have the ability to look at the particle's temperature separately because we're coupling those two particles separately to detection systems, so to quadrant photodiodes where we're measuring the motion of the particle separately. So feedback introduced on only one of the particles, but we can look at the temperature of each particle separately. That's what I'm plotting here, the temperature of the particle that's directly cooled on the x-axis, and on the y-axis, the temperature of the particle that's sympathetically cooled. And so what's plotted as a straight line here is y equals x, just because that's what we would really like to see, that we match the temperatures, and we in fact see that from our data. So this is for all 6 motional modes that are the common motional modes of the two ions. So we have 4 modes here in this plot and the other 2 in this plot. So these are the 2 x modes and 2 y modes and 2 z modes here. And you see that they all line up along this plot, where you can see that if you start at room temperature, 300 Kelvin, so with no cooling, they're the same temperature, and then you should kind of look from right to left as we increase the cooling strength, and we just see that we cool one and the temperature of the other tracks. This is done with the modes individually, but we can also cool all 6 modes, all 3 directions at the same time. That's because the frequencies are all different, so we can kind of separate out the frequencies to set up the feedback separately, so each mode gets its own little red battaya, and then we combine those frequencies back together for a feedback signal that we apply to an electrode, which has an overlap with all 3 axes. So here you see a picture of room temperature, power spectral density, and then the orange shows you the power spectral density after we cool the motion of all 6 degrees of freedom. You might see here this has 20 Kelvin, so we're cooling from 300K down to 20K. It's not, it's still in the Kelvin regime. That's because we're doing these experiments actually 10 to the minus 3 millibar. So pretty high pressures, just again because we wanted to kind of explore this pretty quickly, and working at higher pressures, then if we lose particles, we can just kind of get back and play with them quickly. So proof of principle demonstration, but no reason why we can't map it down to much lower pressures. But you might keep in mind that I've been arguing to you that this idea of the ion trap was letting us get rid of optical fields that could be detrimental, especially in the future in the quantum regime. And I've nevertheless been telling you a story about optical detection. Now, this optical detection is more than 100 times weaker than the kind of focused beams that you would use for optical trapping. So it's true that we've taken out almost all of the light that's going to cause problems with optical trapping. But there is still an optical field, and so if we want to be purists about this, we can say, well, can we get rid of everything optical going on here? And we could, and again, this is not a new idea. Here's a paper from Damel from 1969. So the motion of a charged particle is going to induce a current in the circuit. One can detect this current with a tuned RLC circuit. This has been done in Paul and Penning traps decades ago, and this provides a signal for resistive cooling or feedback cooling. There's also, for example, beautiful work in Hartmut Hefner's group at Berkeley, where they've kind of recently looked at coupling in ions in separate tracks, again, via an electrical coupling. These are simulations that we did a couple of years ago. This was a collaboration with James Millen at King's College London now, and his group is really focusing on implementing this kind of electrical cooling for ion traps. So this is just simulating this feedback gain in the cooling process for different resistances and different charges on these particles, and seeing that it behaves as we expect, and seeing that kind of based on the temperature of the resistor for resistive cooling, we would see a damping that we would expect. So finally, I want to turn to the possibility of including an atomic spin here. And so I've been talking about nanoparticles, and in particular about the motion of a nanoparticle in a harmonic potential. And we have this vision to bring it down to the ground state, but in the end, that's still a harmonic potential. And in particular, the interaction of that nanoparticle with an optical field, this optomechanics that I've used as a motivation, this description is, it's a linear Hamiltonian that's going to describe that interaction. And so even if we can get to the ground state, this is still a thermal distribution described by an average phonon number less than 1. Trapped ions, however, or two-level systems in general, could provide a nonlinear element that would let us prepare non-Gaussian states. And there have been really nice proposals, for example, by Oriol Romero-Izard and Ignacio Chirac along these lines. I don't have time to describe them to you, but that's the key idea, that we introduce a nonlinear element here with a trapped ion. And so what we've been working on, we've trapped an ion and a nanoparticle separately in the same trap. We're working on trapping them together based on a proposal by Chris Foote about how you can trap particles with two very different charge to mass ratios in the same trap. And we're also building an optical cavity with the aim of coupling both particles, that is both the motion of the nanoparticle and the the motion of the nanoparticle to the cavity field, and also the two-level system of the ion to the cavity, that is the dipole interaction between the ion and the cavity. So to wrap up, I've described to you that a nanoparticle in an ion trap under ultra-high vacuum is a high-quality factor oscillator. I've shown you how we can efficiently detect the position of a nanoparticle via self-interference or self-homodyne. I've also argued that efficient detection is necessary for effective cooling, which is going to be necessary if you want to get into the ground state. And I've told you that sympathetic cooling is not just for ions, but also has some really nice benefits for nanoparticles. And finally, I've argued that an auxiliary qubit provides a route to creating non-Gaussian motional ground states. So I've just kind of sketched out that possibility for having these hybrid systems. And I wanted to show you these pictures along the way. That was the high-Q oscillator, this kind of highly efficient self-homodyne cooling, detection, or cooling, this was the highly efficient self-homodyne detection, cooling based on that detection, and also the sympathetic cooling. And so to come back at the very end towards this vision, this is where nanoparticle systems are now. With optical systems, we're not yet at the ground state with ion traps, but we have a clear route there. And I think one of the really compelling reasons for using ions and nanoparticles and ion traps is in terms of this roadmap forward, that the control and capabilities that we have, and in particular the decoupling from the environment and from the optical fields, will really open up possibilities for preparing really fun quantum states. So with that, let me show you the people working on the experiment. So it's about kind of half of my group is working on these optomechanics topics, and in particular, Dmitry Bykov is the senior postdoc, and Lorenzo Dania is the senior PhD student who have really led this work, along with master students Katharina Heidegger and Max Moisberger. Florian Goshin is a newer PhD student, and Nina Earhart is also a new master's student. We've collaborated on this project with Rainer, Giovanni, and Gabriel. And I want to advertise, of course, that we have positions available in my group, and also for separate experiments on trapped ion quantum networks. So thank you very much.
Very cool indeed. Of course, Bill. Maybe let's have a question from someone else. We'll come back here. We'll go to that person.
So sorry, I didn't.
Can you speak up, please? So the question is, what makes the quality factor for these trapped nanoparticles so much higher than for ions?
Yeah, so actually it's a good question what the quality factor is for ions, right? And we were kind of looking into measurements there, and what, there's a range of different measurements, so I think I don't have at the tip of my tongue the best ion measurement there to do that fair comparison for you. And I would also argue, so I think ions you can also get it's the same story. You're in ultra-high vacuum, it's oscillating, so depending on damping mechanisms, but I don't think there's a clear argument why it should be better. They can both get you into very high regimes. Yeah.
Okay, another question.
Oh, sorry, to repeat that, the second part of the question was that the charge to mass ratio is significantly smaller, and my answer was yes, and so you can think about that as the scaling. So, right, in this case I said 10 to the minus 17 is the mass versus so it's kind of 10 to the 8 larger than say a typical ion, and then maybe we have kind of thousands of charges versus one charge, so kind of 10 to the 5 there in the charge to mass ratio. And you can think about that as kind of a volume scaling for the mass versus like a surface scaling for the charge.
Okay, we'll go to Bill.
So first, picking up on the last question, one of the things that comes to mind is that the mass ratio between the background gas and the ions is a whole lot better for transferring energy than for the nanoparticle. Is that one of the things that might make the nanoparticle have a much bigger Q?
So the question, right? So about the mass ratio seems to be beneficial, and I think that makes sense as well. Yeah.
Okay. Now the other question, the one that I was thinking of before, is, okay. So what temperature do you need to reach in order to be in the ground state? And I realize it depends on how stiff the trap is and all that, but for the things that you've got or envision getting soon, what temperature are you shooting for?
So the kind of what's the correspondence between temperature and phonon number?
Yeah.
So this kind of 10 millikelvin is about 10 to the 4 phonons. So then that would say that kind of 1 microkelvin gives you kind of.
So now I'm wondering if you talked about doing feedback on the currents induced and doing resistive cooling and all that, but of course that also means that you're doing resistive heating. And so does that mean that you would have to cool your trap to microkelvin, or is there a long enough time that if you've got something beating it down to microkelvin that you can suffer the fact that you're weakly coupled to a much hotter reservoir through the electrodes?
Right. So if you wanted to do resistive cooling, the temperature that sets that is going to be the temperature of your resistive element. And so the way to do that, right, which is done, for example, in the past with a penning traps, would be to use a cryogenic resistor. That would be one route.
Right, but that's only gets you to millikelvin.
Exactly. And so I guess I would also say that's that would be why we thought about it, but it's not a technique that we're pursuing right now, because I think I'd rather see, I think that the optical route is a clear optical detection and electrical feedback, or optical feedback, but is a clear route that gets us to the ground state. And so I'd like to stick with the optical detection until we see that it's really causing us a problem.
Right, but what I'm also worried about is, what about the fact that you're coupled to a reservoir that isn't going to be any colder than millikelvin, even if you put it in a dilution refrigerator, and you're probably not going to do that unless you really have to.
Yeah, no.
So are you going to be okay because the coupling is weak enough?
Yeah, so right. So even if we're not trying to cool, the fact is we still have that coupling. The detection is still going on, even though if we're not measuring that signal. I think that's, so we haven't done that calculation, is the short answer. And I think it's important to keep in mind and worry about.
Okay, we have a question from back there.
Hi, is there an interesting way to kind of use the internal degrees of the nanoparticle? And if yes, how would you cool those?
Yeah, so that's a great question. So there's, so first of all, yes, and one idea would be to go back to this concept of saying that you want to introduce a two-level system in order to introduce a nonlinearity into the optomechanical interaction. And so I made the argument, okay, let's take an ion and we'll couple it to the nanoparticle, so the ion will be outside, and we'll couple them both to an optical field. But you could also say, well, let's put this two-level thing inside the nanoparticle. For example, if you had a nanodiamond with a nitrogen vacancy defect inside. And so, and then you would also care about this internal degrees of freedom. And in particular, you would also want to, cool internal temperature. So there's been refrigerative cooling that's been shown in Peter Barker's group at Imperial with nanoparticles that kind of gets, I think, sort of from hundreds of Kelvin down to Kelvin. But there's a lot more to explore there with those refrigerative cooling schemes. And we are kind of just getting started in that direction. To look at particles that aren't just silica, but that have also these kind of internal degrees of freedom as well.
And what about like the global rotation of the nanoparticles?
Yeah, so again, right, you don't have to restrict yourself to center of mass. You could look at, for example, Gabriel Hété's group in Paris has looked at librational modes, also Tongkang Li at Purdue. So people have looked at libration and looked at even at rotation. And you can also think about, you know, if you have particles that are not spheres but are rods, there's a lot of degrees of freedom to look at there. In particular, you can cool that libration as well to the ground state, and there are arguments why that might be a nice route as well.
Okay, thanks a lot.
All right, let's thank Tracy again.